Welcome, this is Mrs. Nearing, and we're going to go over some more of these buffer problems from page 13b. These are from the textbook, and we already talked through a few buffer calculations. 39 is another example of calculating the pH of a buffer, and remember with these examples, you could either use the Henderson-Hasselbalch equation, which is pH equals pKa plus log A minus over HA, or you can use an ice chart and a K expression. So either one works. In this first problem, the HA concentration is 0.135 molar. So you're going to recognize the conjugate acid because it's the one that has more hydrogens in it. And then this right here, this ionic compound is a source of ClO minus. That is my conjugate base, and it has a concentration of 0.155. So when I'm setting up my Henderson-Hasselbalch equation, my HA is going to go on the bottom, 0.135. My A minus, 0.155, is going to go on the top. The Ka I got from that table of Ka values off to the side in the textbook. Problem C requires a little bit extra work because you're given grams first. So first you have to take your grams and do a gram to mole conversion using the molar mass from the periodic table. So that's PT for periodic table. And then once you have moles, you're going to divide it by liters to find molarity. So the liters in this case is 150 milliliters, so that's 0.15 liters. So you're going to convert both of your gram values into molarity values, and then you can plug it into either the Henderson-Hasselbalch equation or an ice chart and solve for pH. Looking at a problem like number 43. Again, with all these, you either use Henderson-Hasselbalch or an ice chart and a Ka expression. In this one, Henderson-Hasselbalch might be the easiest way of doing this one. So Henderson-Hasselbalch again is pH equals pKa plus log of A, which I'll plug in what this is, F minus to HF. So that's my weak base and conjugate acid pair right there. So I know I want the pH to be 4.00, so I can plug that in. The pKa is the negative log of this number right there, 3.5 times 10 to the negative 4. So I'm actually going to plug that in my calculator real quick. 3.5 e negative 4. So it looks like the pKa is 3.46 plus log F minus over HF. And the question just asked me, it doesn't ask me to solve for F or HF, just asked me to solve for the ratio. So I'm just going to rearrange this so that I can set up to solve for the ratio. So log F over HF equals 4 minus 3.46. So that is 0.54. And that is, so the log ratio is 0.54. So to find the actual ratio, I need to take 10 to the on both sides, okay, which means that's written a little bit messy. That basically means the ratio of F minus to HF is going to be 10 to the 0.54, and that's how you get your ratio there. So using your Henderson-Hasselbalch. A problem like number 45 is a lot like we did in the lab, where you're trying to calculate how many grams of the solid conjugate base you want to add to your acid solution. So the first step, I'm going to change my color of pen really quick because the red is bothering me. First step is to do like we did above and solve for the ratio of my acid to base. So I'm going to use this pH equals pKa plus log of A minus over HA. And I want my pH to be 4.25. I'm going to plug in the pKa, which is the negative log of 6.5 times 10 to the negative 5th. So that is 4.19 plus log A minus over HA. So pH is already pretty close to the pKa. So I'm going to end up with A minus over HA equals 10 to the 4.25 minus 4.19, so that is 0.063. That's going to be pretty close to equimolarity here. So actually, I'm going to plug this in my calculator. 10 to the 0.063. This ends up being, 1.16 ratio. So they're almost equimolar. So what that means is, if you can rearrange this, A minus is 1.16 times the molarity of your HA. So if your HA concentration is 0.15 molar, and how do I know that? Because it tells me that's already set. I want my A minus concentration to be 1.15 times that. So that's going to be, I'm just going to write this down, 1.16 times 0.15. That will give me my molarity of my A minus. And how does that help me? I want to find grams, right? So if I know a molarity and I know a volume, so I can multiply this by my volume, which is 0.15 liters, that's 150 milliliters. That's going to give me my moles of my conjugate base. And then the conjugate base here is sodium benzoate, so I'm going to multiply it by the molar mass. The tricky part here in the book is they didn't give you the chemical formula of sodium benzoate. They're supposed to note that since this is benzoic acid, I guess, that this is the benzoate anion right there. So if you just remove the hydrogen and put in a sodium instead, you will get sodium benzoate. So even though all we want is this anion right here, when we're using the molar mass, we have to include the mass of everything, okay? Because that is the form in which the benzoate ion comes. It comes paired with sodium ions. When this thing dissolves in water, it's going to dissociate. The sodium ions become spectators. But we do need to consider their masses when we do the molar mass step here. So we're basically, the first step is find out what our molarity of sodium benzoate needs to be, convert your molarity to moles, convert moles to grams, and that's going to tell me how many grams I need to add to my solution. Again, this is very similar to what we did in the buffer lab. You calculate how many grams of solid to add to your buffer. And then the last question right here is, what buffer is the best choice to create a buffer system with a pH of 7.2? So in order to have a buffer, you need to have a weak acid and its conjugate base. And it looks like all of these are weak acid conjugate base pairs. We got NH3 and NH4. We've got HC2H3O2 and then just C2H3O2, HClO2 and then ClO2. So they're all conjugate acid base pairs. Check. The other thing that we want is we want the pH, desired pH, to be close to the pKa. So we're going to look over here at our table of Ka values and figure out which of these is going to have a pKa close to the pH. And this is a good thing to be able to do without using a calculator. So I can kind of eyeball this. I'm going to look at acetic acid and say the Ka value is 1.8 times 10 to the negative fifth. What that tells me is the pKa here is going to be between 4 and 5. And that's just kind of how log rules work. So the pKa is going to be pretty close to the exponent right there. For chlorous acid, based on this number right here, the pKa is going to be between like 1 to 2. Over here, the pKa, if I plugged in my calculator, is going to be between 7 to 8. So it looks like this right here is going to be my best bet for a buffer system because the pKa is going to be closest to 7. These other two are pretty significantly different from that. So what was that one? That was this one right here. So this looks like my best buffer system. All right.